What's this? Oh.
Alright, y'all, by now, you should have your notes out in front of you, and you should be looking at this do first. I'm going to pass around the pre-cal inbox, if you can pass it from table to table, and if you have your problem set, you can put it in there. Other than that, you should be working silently on this do first. So I'm going to ask for voices off during this do first. I'm going to ask for voices off during this do first, so that we're focused while we're working. So make sure we're not talking, because I don't want to have to give out any demerits.
Or no?
I'm confused about the question.
Like, because last week I got the thing for the 10.
Gotcha. No, I've got my list of people. I just, well, when I heard it tonight, I'll look up my list. I don't want to know my list. So I was confused with what you were saying. So again, unless you're just quietly like passing and you need to talk about, oh, I need the pre-cal inbox or whatever, other than that, our voice should be off while we're finishing working on remembering rules of exponents. Israel, Felix, Edith, Eli, Dahlia, Stephanie, Diego, Jamie-Lynn, Sandy, Brandon, Brian, Juan Carlos, Martin, Ned, Kennedy,
Here.
Giselle, Leo, Gustavo, Lirio, Tyler, Melanie, Lazaro, Jonathan, Messiah, Joanna, Kevin, Ehong, Christina, Johnny, Luis, Deanthea, Brian. Okay, while you keep working, I am going to pass back what I have graded of the unit exams, and so you are going to get back. Quick. I'm gonna pass back to you.
Great.
I'm gonna pass back to you your test first, which actually is not gonna have like the score on it. It's gonna have just the points that I gave to you, and then you're gonna get, like last time, one of these score sheets that actually has then like your 8 point whatever or whatever. Okay? So at first, when you're looking around, you're gonna be like 35 points, but just hang with me, okay? So keep working on this, and then as you get your test, you can also be looking at that and reviewing what you got and what you missed. get your score sheet too. Okay, you're going to get another timeline sheet by the end of the day.
No, this is not
I hope you were, because I don't think you were. I don't think it Johnny, yeah, Johnny wanted.
Wow, you left those.
I think they're going to. So I guess yeah, you can do it out. That's
what I get.
It's already. I just have to. I'm just that excited. It's okay. What's the average in there? I'm good with that.
Okay, did anyone not get their
This
score
one has
sheet?
to do with like, it was the end of the class. I was
Not
like,
get their score sheet?
like at the end of the class, I was still working on it. I was like it's right.
What the hell?
I was like, this one's important. No.
Okay, did anyone, one more time, did anyone not get their score sheet?
I think I got the wrong one. I always be like, follow my instinct.
Okay, eyes up here for me, voices off. I'm going to talk a little bit about the test for a second. Okay, so on the test, in general, I had very high scores on the test. So I, as a result, didn't curve like nearly as much as unit exam and not much compared to even how I've been curving quizzes. So taking a look at your score, for the most part, that was fine for most people, but there were like some of you guys that I know like might be like, ooh, on one or two of the standards. And that's probably because like it's pretty close to like your raw score this time, which means even to be like in the 7s might be an improvement from what you did on the quizzes that I kind of like curved, just kind of depending. The numbers were kind of weird. But a lot of people too did really well on the last quiz on Unit 2. So even though the scores on the unit test were high, a lot of people FA'd their scores from the quizzes, but not everyone, just because a lot of people already had like 9s and stuff on the quiz. And so to FA a 9, you have to have like a higher 9, which is like just starts to get difficult. So if you're curious about where that put you landing for your average, the progress report, I want to emphasize the progress report you got home today is even before the quiz we took last week. Like we submitted grades last Tuesday and it just takes them off and then we process them to print the progress reports. And so at this point, that isn't a great representation anymore of your grade because we've had the quiz and the unit exam. So I encourage you to check your overall average online again, or if you don't have access, come meet with me so I can like talk you through where that puts you like overall in pre-cal, okay? But most people are in a pretty good spot, and I would love to one-off with you if you're disappointed in where you ended up, and we can talk about kind of like what happened with that. If you take a look to kind of recap, since we've only had one unit test before, on your score sheet to kind of remind you how that works. Each of your 2 scores, you can look underneath, and I have listed out which questions went to standard 3, which questions went to standard 4 with our standards-based grading. Okay, so you should be able to go through your test and see which ones you got and which ones you didn't for each standard, and why it gave you what it gave you. All the multiple choice answers are there for you to access and look as you check through your test, and then your marked up free response should help you with seeing what you missed there. With this, you probably noticed when you came in, we usually get our notes on Monday, and we usually get our problem set, but you didn't have a problem set to grab today. So make sure you turn in the one that was due today, by the end of the day, but you didn't get a new one for tonight. What I want you to do tonight is work on a correction, like I think I mentioned last week that we'd be doing, on your unit test, so that I kind of want to get another grade in the grade book to kind of like help people out with this test if you put in the effort on your correction. So, if you look at your score sheet, I'm going to kind of explain what you're going to be doing on your correction. It looks something like this on the bottom. Yeah? Okay. Your task for tonight, we don't have a problem set. You're going to get a problem set tomorrow, but it's going to be shorter because I'm giving you less time. So it'll be a nice short one this week. Because tonight you have another task. Your task is going to be to do a correction from your unit exam. So notice I said correction, which means you get to choose one problem out of all the problems that you might have missed that you feel like you want to really like dig in tonight and examine and make sure you really understand inside and out. And you are going to do a full-on correction and reflection on that problem. So I'm going to talk through like the things I'm going to be looking for when you turn this in tomorrow. Right here it obviously says the problem number because I need to know which one you're talking about. So write down the problem that you choose. When choosing a problem, I'm not looking for you really to do a correction on one that you made some sort of like silly mistake. If you look at it and you're like, oh, I knew how to do that, and then I forgot that one negative, like I don't want you to do a correction where you're just fixing a negative. I want you to pick a question where you felt like when you looked through your test tonight, you remember when you got to that problem, you were struggling with it and you weren't sure what to do. And tonight I'm giving you the extra time to go figure out what to do by either talking to each other, you all have your test back now, coming to talk to me, anything like that. Okay? Question?
What if all of your mistakes are silly?
Then, like, you still need to do a correction, so you can pick one of those. But I'm just saying I want you to use, when you're looking at this, use that as a guide of I want to pick you the most where there's something for you to learn from, rather than if you have one that, like, you completely had no idea, and then the one where you missed a negative, I want you to pick the no idea one for yours, okay? Then, next up, I want you to write your original answer so I can kind of compare your new work to what you thought the answer was before. Because often when you write it, I can like quickly see like, oh yeah, that was all the people that like did this, made that mistake or whatever. If it's multiple choice, that means putting that multiple choice answer here that you answered incorrectly. If it's on free response, it means putting that number that you got wrong here. Or if it's like a graph, like you remember the one on the back of the free response application where you had to draw the polynomial? Obviously I don't need you to draw like your old drawing in that little bitty space. So you can say like C graph if it's a case like that, okay? But I want you to put your old answer, then you're going to go ahead and provide your new work here. So your new work does not mean I want just the new answer, right? Like especially for the multiple choice, I gave you the key, so like it's not very special for you tonight. Go write the right answer here. I want you to provide for me work to show me the like proof or evidence behind the correct answer. That could be in words, it could be with math, like whatever it takes for you to display to me some sort of explanation of the answer. And then last piece, down at the bottom, I want a written, we don't write a whole lot, and so I want to see more of your kind of writing and reflecting about pre-cal. I want you to write to me at the bottom what you learned about your mistake on that problem, because we learn a lot from our mistakes. And that could be a wide variety of things that you could learn or reflect on. What I don't want is, like, it should be like 2 to 3 sentences. And if it's one sentence, it doesn't mean it's automatically wrong, but it needs to be a really substantial, awesome reflection, not like, I learned I didn't know how to do that one, or like, I don't know, something like that, I'm like,
I learned that I was wrong.
So, I want you to really like think about that and reflect and write something. It could be, I realized that I didn't know my rules for asymptotes as well as I thought, and I thought that horizontal asymptotes the bottom was 0, and actually that's my horizontal, actually that's my vertical, blah, 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 blah. So, I don't know, anything you can come up with related to your problem to reflect on and learn from, as we go into unit 3, 4, and on, we're going to continue rolling this stuff and it's going to pop up a lot, so we want to make sure we have a good understanding of what we are leaving behind a little bit, okay? Okay, for now though, I don't want you working on that. So if you can make sure, take the next like 20 seconds and put test and score sheets away, and then I'll collect them again tomorrow to give you a grade on that correction. And then I'll give them back to you so that you can keep your grade obviously long term. Put that away, make sure you put in some time today and tomorrow, and then give it to me tomorrow on that correction. Alright, let's jump in now to Unit 3. So let's go ahead and move to our do first. That's crazy, we're cruising. Do first time. It's also trying to get those participation points for the end of A2. So I'm going to be calling on a lot of people to try to ramp up the champs. So anyone that can help me out on 1, when I put all that stuff together, Brandon, what do I get?
162x to the power of 11.
Whoa.
Oh shoot, I got this wrong. Yeah. 3 to the power of 4, right? 3 to the power of 4 is 81, right? Times 2, what's 81 times 2?
162.
I like literally have it wrong on here, so what is this?
162.
162. Oh! Don't you hate when your marker doesn't work? Someone put this somewhere. Can you, Christina, get the trash can? I'm gonna see if I can make a bucket. Okay, ready? Here we go. Oh!
Don't throw things from the
This
classroom.
weekend,
Miss
I went to this place that had, you know that game where you play the basketball?
Yeah.
And I was playing, you know that one, the like arcade one where you're versus the next person?
Yeah.
And I was playing with my buddy from high school, but he now coaches high school basketball. So then he was like coaching me on my form, told me about my shot pocket and how I need to like fix it and stuff. So I was working on it, but then I hit the ceiling, so I totally ruined that. So oh well, I'll try again tomorrow. Hopefully I get another marker that doesn't work and I can try again. Okay, when I did this, honestly, actually forgot to do the 3 to the 4th power. So that would be 3 times 3 times 3 times 3, which is 81, times 2, he said is 162. Okay. X to the 11, because you have 8 here. 2 times 4 is 8. Plus 3 extras would be 11. Okay? Kennedy?
So it wouldn't just be like you put the 3x to the power of 6 and then do 6.
Be careful, it's not 3x to the power of 6. This would be 3 to the 4th power and x squared to the 4th power. 3 to the 4th power is 81. X to the 2nd power to the 4th power, you multiply those so it's x to the 8th. X to the 8th. Then we have times 2 times x cubed. 81 times 2 is where he got the 162. X to the 8th, x cubed, 8 plus 3 gives us our 11. Okay? Okay. Next up, sorry, that one threw me off. Next one, Sandy, what'd you get?
6b to the 7th power.
6b to the 7th power, lovely. Next one, we've got a fraction, and so we should know what to do with the exponents. Israel?
You just subtract them, so it's y cubed.
Lovely. Moving on, 1 over 2a cubed. You've got to cube everything, Iham.
1 over 8a to the 3rd power.
Cool, so you cube the 1, that's 1. You cube the 2, that's 8. You cube the a, that's a cubed. Okay? Next up, subtract your c's, subtract your d's. What do we get, Melanie? C cubed is correct. And last but not least, another crazy one. Anyone get the last one?
Miss, I'm too dumb for this.
No, you're not. Alright, voices off. Let's talk about it then, because I didn't see many hands on that one. Here we go. Ready? Same thing as the first one. You got to do 3 to the 4th, which we said is 81, squared to the 4th, which is 8th power, right? But then on the bottom, we've got a 9n. What's 81 divided by 9? 9. Good, I heard someone say it.
Oh, that cancels out.
Then if I have n to the 8th and an n on the bottom, n to the 7th. Okay? In a second, I'm going to come around and give stamps to all the people that participated. Thank you. But we are going to move along now to take a look at your calendar. So reminder, your exam corrections are due tomorrow. If y'all can turn those voices off, Brian's table, thank you. Your new problem set you won't get until tomorrow, and those will be due next Monday, but like I said, they're going to be a little bit shorter. But let's take a look at what's ahead in Unit 3. If you want to glance at your calendar really quick. Today, we're going to be doing an intro to graphs and transformations, can't talk, of exponential functions. Anyone ever seen like e to the power of x type things like that? Yeah. Okay, cool. And then later this week, we'll be working our way then into the other part of our unit, which is with dealing with logs. If you've ever seen log before. Don't be too excited, Giselle. Look at that face. She's
No, I thought I escaped that when I left AP1.
nope, it's back. Woo. Okay. Then, moving into next week, on Wednesday, you'll have your first quiz. Middle of next week. So this is a quick unit. It's going to be shorter than Unit 2. So you'll have a quiz on Wednesday. So we're going to learn a lot this week. And then you're going to need to start working on that for next Wednesday. And then the week after that is kind of our testing week. So we're going to be done with this by November 9th, which is coming quick. So I just wanted to put that on your radar as we look at our calendar, because this isn't one of those things where it's like, oh, I'll figure this unit out later, because later is going to be here before you know it. Cool? Okay, so today, graphs and transformations of exponential functions. So we're going to be taking things like this. We're going to be talking about what the graph looks like, and then we're going to be transforming them. So very similar to, remember your foldable, the parent functions, where we took a graph and then we shifted it, and we dilated it, and we did all sorts of stuff. We're going to be doing that, but with exponential graphs. So we're going to learn a new graph, and then we're going to transform it. So we're going to start by exploring 2 examples of graphs that have an x value not as our base, like x squared. X is our base, and squared is our exponent, right? It's a number in the exponent. This unit, we're going to be looking at when our base is the number, and our exponent is the variable. Y'all see a difference there? Okay, so 3 to the power of x. So let's go ahead and we're going to plug in some x values right here, and then graph and kind of see what it looks like when we have an exponential function like this. So let's say our x value is -2. If our function is 3 to the power of x, that means this is 3 to the power of -2. Good thing we learned about negative exponents last unit, because 3 to the power of -2 is not the same as 3 to the power of +2. Does anyone remember what it means when we have a negative exponent? Christina remembers. 3 to the power of 2. So 1 over 3 to the power of 2 is what this means. So 3 squared is 9, but it's 1 over 9, so 1/9 would be the value of the function.
Stop it.
Yes? Okay, we're going to cruise through the rest of these to kind of speed us along. Writing that down. 3 to the power of -1 then would be 3 to the power of 1, 3, but 1 over that, so 1/3. Yeah, Deanthea, whenever I have a power of 0, 3 to the power of 0, what is it? Not quite. Oh, sorry, I misheard. I know. I misheard. It's 1. Anytime you have a power of 0 as our exponent, then it's going to be equal to 1. Then we've got 3 to the power of 1, which is 3. And then 3 to the power of 2, which is 9. Okay, so let's kind of sketch. It's kind of weird because we have to graph some fractions, but let's sketch this and kind of see what an exponential graph is going to look like. If you have a -1, -2, and I know yours is kind of smaller grid, so if you want to count by 2s, you could try that, or you can just kind of scrunch it up. Let's say this is 1, 2, 3, 4, 5, 6, 7, 8, 9. Mine fits like that. Y'all can just take a look at yours. At -2, I'm not even to 1. I'm at 1/9. I'm like pretty darn close to 0 right here on my graph because I'm not even up at 1, right? At -1, I'm at 1/3. I'm slightly bigger than 1/9, but still not even up there at 1 yet. I'm still really close to 0, right? Okay. At 0, where am I? 1, so I'm finally on my first line of my y values going up, right? At 1, I'm going to go up now to 3, and then at 2, I'm going to go all the way up to 9. So notice that these graphs, Juan, plot those points for me, start as really small fractions close to 0, and then they get bigger really fast, and all of a sudden your graph shoots up there to 9 before we even get to very big x values, right? You can only imagine by the time you get to 3, 4, or 5, you're cubing to the 4th power to the 5th power things. It's going to get really big really fast. Okay? So notice, moving from the left to the right, if I were riding this like a roller coaster, is it increasing or decreasing? Increasing, like we learned in Unit 1. It's increasing really fast. This is going to be what we call exponential growth. You might have heard of exponential growth. Things that grow exponentially are going to grow quickly like we see this graph. Okay? Okay, using that, I want you to go ahead and try 3 to the power of -x. I want you to plug in these different values of x and then graph your function and see what it looks like. Okay? Go for it. Raise your hand if you're a stamp person. Hey, you want to see anything?
I never got this.
I just said, do you want? I was like, yeah, I want.
Anyone else over here? Cam?
You don't know from last week.
Oh, you want Israel?
Yeah.
Okay, I'll put 2 in there. I think I remember because you said, but I didn't have them.
You the other one.
So this time it's 3 to the power of -2. What's -2? +2. So 3 to the power of 2. Do we really? Where do we use mine? Mine's really bad about the little end. Sorry, the little end thing.
You can't have -0.
Okay, as you wrap that up, you can check right here. What do you notice? Right, like the negative became positive, the positive became negative, so it ends up like reversing, which means if we graph it, on this side, we're up here at 9 and 3, and then on this side, we're getting to those small little fractions, so your graph should look something now like this, right? Okay, so if the other one's exponential growth, it's getting bigger. This one, if we go from left to right, like a roller coaster, it's decaying quickly. This would be like a roller coaster where you're like, woo, like going straight down. And so this is what we call exponential decay. And tomorrow we're going to do a lot of exponential growth and decay, like word problems where you see situations where things are growing or decaying exponentially. Okay, so in general, something that has this form, or this form where we have a base and then a power that's a variable, is going to have exponential growth or exponential decay, and your graphs are going to look a lot like this, okay? So let's go ahead and record some of the characteristics of our graph, because we're going to see these a lot, and we're going to need to refer to them and describe them. So if we're talking about domain and range, y'all start right there on the bottom, and then the rest awkwardly goes on to the next page, so sorry about that. But we're going to start with domain and range, and then asymptotes, intercepts, and behavior, you'll see, are at the top of the next page. Domain and range. If this is my graph, it goes forever in this x direction, right? So negative infinity, all the way. There's no stopping point, because as this goes up, it's also going out forever. So it goes from negative infinity all the way to infinity. For your range, now think about y's. It does not go down forever. See how it's like leveling off right there? Yeah. So there's no negative y values here. it starts at your horizontal asymptote, which is at 0, but it never actually equals 0. So it's going to be parentheses on your 0, and then up forever to infinity. Yep.
So it's like for all infinity in the back, it just doesn't ever equal 0, it's just like non-existent, and then it starts going up?
Because think about, like, if you were to increasingly put negative x values, like if I had 1 over 3 to the, because remember when we had like negative, let's say even like 100, it would be 1 over 3 to the 100th power. This is just going to be a really big number that we're splitting 1 by, so it's a really, really small fraction. So they're just going to become smaller and smaller and smaller fractions, but it's never going to be equal to 0. It's like you take a cake and you cut it into 3 pieces, and now like a third of the cake is smaller, right, than the original. And then you cut it again, and it gets smaller, and you cut it again, and it gets smaller, and you cut it again, and it gets smaller. But you could cut up into smaller pieces, which means like I'm cutting it up into increasing pieces, but the cake's not ever gonna like go away. You could have a little crumb, and you're still like cutting it into like little pieces. And it's practically 0, right? If I give you like a little crumb, you're like, nothing, no cake. Because it was like a really teeny crumb. Don't like my example? But it's still physically there. It can't disappear. You're still cutting it, okay? Okay. Asymptotes, we just talked about that a lot. It's approaching 0, y equals 0. The horizontal asymptote. Did you drop something, Kennedy? Oh, paper clip. Bothering her. There's a paper clip on the floor. Y'all help her out. Okay, intercepts. Where is it intersecting the y-axis? At 1, so that's the point 0, 1, x is 0, y is 1. And then last but not least, our end behavior. Let's talk about those limits. You noticed on your unit 1, 2, what test did we take? Unit 2 test. I asked you for the end behavior using proper limit notation, which meant if your limits weren't perfect with the lim and with the x approaches and all that, then you missed this point right here. So let's make sure you have everything. For the left, it's the limit as x goes where? Negative infinity. So the limit as x goes to negative infinity of, you have to write the function f of x to tell me that you're taking the limit of that function. See how on the left it's approaching that asymptote, it's approaching 0. Okay? For the right side of my graph, x is approaching infinity, and where's our graph headed? Up to infinity. So as x goes to infinity, our y value is also going up, up, up to infinity.
And beyond.
That's your infinity and beyond. That's your left and your right hand behavior in limit notation. Okay? Okay, now we're going to come back to the thing at the bottom. But let's go flip back to 3 to the negative x. Notice, even though it used to be like this, going up over here and leveling off right here, when I flip it, I'm still going to have the same domain and range because I'm still going both directions of the x, and for the y I'm still starting at 0 and going up, right? That doesn't change that. Does it change our asymptotes at all? Or our asymptote, there's only one. No, our asymptote's also the same. So let's write that down. Let's see. Eli, if you take a look at the graph, does it change our intercept where it crosses the y-axis? No, so that's also going to be the same. Everything's very similar with our exponential decay, except now that we get to the end behavior, it's no longer leveling off on this side. Now it's leveling off on the right side. So 0 is going to be this limit, right? And then instead of going up on the right, now it's going up to infinity on the left. So this is going to be on that limit. So you'll notice your limits, your answer is going to change from left to right for exponential decay. Okay? So it's important to be familiar with these graphs and familiar with the characteristics, and know that 3 to the power of x we said is an example of exponential growth. It's growing. And so 3 to the power of negative x is an example of, fill in the blank.
Exponential decay.
Yes. She's really good at doing that whenever I do it fast. Exponential decay. Melanie's always got it. I should give you tests like in speed versions. You could answer really fast.
I'm
She's
gonna
good
be
at that.
absent all those days.
Okay, cool?
Yeah.
Alright, so below you'll see a big blank box. Okay? Originally in this big blank box, there was a table from your textbook, or from the resources that we use, that had the graph for exponential growth and the graph for exponential decay in general form. So we just looked at specifically 3 to the power of x, but like the general one. But I think it's really important because we're going to see it so much this unit. And I'm even going to make a poster, I just didn't have time this weekend because I was out of town, that I'm going to refer to like the whole unit. So as a result, I think it's going to be good for y'all to like physically draw it and write it down rather than just reading over it, so that all these things are getting in our head. It's going to be very similar to what we wrote right here, but the more you write it and see it and process it, the more familiar you're going to be with these graphs, okay? So we're going to split our box in half. We're going to do growth on one side, decay on the other. So split your box in half. Let's start with exponential growth and talk one more time about what our graph looks like for exponential growth. Our equation in general form, we saw one example is 3 to the power of x, but it can be any equation that looks like this, b to the power of x, where b is some number bigger than 1. Like for example, was 3 bigger than 1?
Yeah.
So 3 to the power of x was exponential growth. That means 2 to the power of x is also going to be an exponential growth graph. 100 to the power of x is also going to be an exponential growth graph. The cool thing, it got to be bigger than 1, not equal to 1.
Okay.
So it got to be bigger. So 1.1 and on, or whatever, 1.0001, but not 1 itself. Okay. So if that's the case, your graph every time is going to look very similar to the graph you just saw with 3 to the power of x, where it has this general shape that approaches 0 and then heads off to infinity. And the cool thing is that no matter what your b value is, it also every single time is going to cross at 0, 1. Because think about it. If I put 0 in for x, all of those would be equal to 1, right? So no matter what your base is, this is where it's going to cross, and then it's just going to grow in the same general shape, okay? So they're not the exact same graphs, but all these characteristics we're listing right now are the same, okay? Okay, so because it's exponential growth, we also can see that since it has that shape, we should know its domain and range and be really good at referring to those. So what's going to be our domain? Who said that? Johnny, you get the credit. I'm going to bring you a stamp. Negative infinity to positive infinity. And then our range. Tyler, where does our range start? What do you think?
0.
Good. 0, and then it heads off to infinity. So this is good. So we're writing it ourselves so that it's soaking in our brain a little more. We're going to be more familiar. 0 to infinity. Okay. Our intercept is going to be, like we talked about, no matter what our base is, it's always going to be, when we plug in 0, we're going to get 1. Our asymptote, because it's going to get smaller, 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 and smaller, but never actually make it to 0. It's approaching 0, so that's what we call our asymptote, y equals 0. And then last but not least, let's write our end behavior. So the limit as x goes to negative infinity of f of x. As we go to negative infinity, that's this side. Where's it going? It's approaching the asymptote, right? It's leveling off at 0. And then on the other side, it's going to infinity. So just filling in these because you'll see them a lot. We just saw it with 3 to the x, but it's actually going to work for any b to the power of x where b is bigger than 1. Lovely! Such pretty notes. I like having it all written yourselves. Okay, let's talk about decay. And you're going to fill out most of this one on your own actually. But decay. Our equation for decay is going to look like what? It's not going to be b to the power of x. Who can recall in our last example when our graph did not grow, when it decayed, what did it look like? Love all the hands. Jonathan? B to the power of negative x is going to make it decay. Or, I'm going to write another form so that you guys can always make sure you're recognizing. You got another idea, Deanthea?
Is it the 1 over the x?
Right? Like this is the same thing as anytime you see a fraction, 1 over b to the x, you need to recognize that that's the same as a negative exponent, and so these are both decay, fraction or a negative exponent, where b is greater than 1. So for example, 3 to the negative x, that one we looked at is actually the same as this, and so you need to be able to recognize them both as decay. Yep?
So if b is less than 1, that's like a profession or...
So if it's like a negative value you're saying or something?
Yeah, if b is less than...
So we're going to be doing some reflecting when we have negatives, but it's going to come from these two main graphs. Yep, cool. Okay, so from that we know the graph looks like this one that we saw for 3 to the negative x, and it crosses at 0, 1. And you should be able to write down again your domain, intercept, all of those things. All of them are actually going to be the same, remember, as growth, except for what? End behavior. The end behavior should switch. So go ahead and write one more time, because the more you write it, the better it's going to stick in your head. Go ahead and write down the domain, range, intercept, asymptote, and end behavior of that exponential decay. And see if you can do it, maybe without just looking at the other side, to see if you could do it freehand. If I asked you what is the domain of the graph, you could just say it. So this should be infinity now, and this should be negative. So I've got these in the same spot. This is my left, so this is negative thing. This is my right. This is x is going to infinity, it's 0. So if you keep the limits the same, your answer, what y is 0, switches. But your limits are the same. Okay? Now for you, make sure you write x is going to negative infinity. Right here. It says minus your little notation. If not, that's what just on the test I just wanted because the limits didn't have all the limits. Okay, we got that one? I'm not going to write them all out because y'all have them matching the other side, but then the limits on the left should be going to whatever, infinity, on the right 0. So the answer is going to positive infinity as x goes to negative b. So, but your answer is positive. It's still going up. Even though it switched to this direction, take a look, it's still going up on that side to positive infinity, right?
Yep.
As x is going up to negative infinity. Okay, cool. Moving on. Sorry. That's all stuff that you would have just been looking at. Oh, don't look at this yet.
I want to take a sleep.
Look right below. Okay? if you look below, you see two little graphs. We've got, sorry, technical difficulties. I tried to hold it in the last class and then it got really hot and I nearly burned myself. Okay, if you look below, you've got two functions that are exponential graphs of some sort, except now we're going to do transformations. So eyes up here. Remember x squared? We started with our parent function x squared. Who remembers what happened, what we said it would happen, if you now look at x squared plus 4? Raise your hand if you can tell me what would happen to my graph of x squared if I add a 4 on the outside like that. Kennedy?
The graph will translate upward for you.
Cool. 1, 2, 3, 4. We'd start, instead of at 0, 0, we'd start right there and our graph would look like that, right? Okay. So based off of that, I want you really quickly to talk to your neighbors with these bottom two graphs. I want you to look at what transformations are happening to 2 to the power of x. And I want you to think about where the graph's going to be moving. And just be ready to describe it when we look at my examples up here. Okay, 30 seconds, talk to your neighbors. What's going to happen to the graph? You don't have to perfectly sketch it, you just need to talk about where it's going. Up, down, left, right, stretch, compress. What's happening to your graph? 10 seconds. Okay. First one. 2 to the power of x plus 4, where the x plus 4 is inside up on the little exponent. Who has a guess of where this one is going to go? Kevin does.
I believe it will go to the left, maybe?
To the left 4. Yeah. When we add 4 on the inside, it doesn't go forward 4, it goes back 4, right? Yeah. So it should go back 4, okay. What about if I add 4 on the outside? 2 to the power of x plus 4 separately. D'Anthea?
Go up.
Should go up 4, just like our So take a look. I graphed them on my calculator. You can take a look right here. The tough thing about these graphs that I noticed with people last year is because x squared is nice and starts at 0, 0, and you can move that like starting point around. This graph has like kind of a harder reference point. A lot of times I use that we started with our intercept at 0, 1, right? And then that interception point is no longer an intercept, like our intercept is randomly up here on the graph now, right? But it moved over 1, 2, 3, 4, and now that point is right here at -4, 1, right there. But it's not like a starting point of our graph, it's just like that point on that like curvy part where this is still, notice, a gap of 1 from that point to our asymptote. And our asymptote is still down here at y equals 0. And so our graph looks something like this. Okay? On the other one, our point used to be right here at 0, 1, but then D'Anthea said it should go up 4. 1, 2, 3, 4. Now it's right here, but be careful, it's not at 0, 4. It started at 1 and went up 4. It's at 0, what? 5. Which is why it kind of like tends to mess people up, because people think it should be up at 4, but it should be up at 5 because earlier it was at 1. Right? Okay, so stick with me. Don't pack up yet. Eyes up here. Okay. One of the ones that we're going to see a lot, is our base is not going to be 2 or 3 or like the ones that we just saw. Our base a lot of times is going to be what we call the natural base, which I wrote up there at the beginning. It's going to be this number E. E is just a special number, 2.718, kind of like pi is 3.141, that we see a lot. I'm going to let you out on time. Is this number bigger than 1? Yes. So it can absolutely be our base, and our graph should look the exact same, right? And then we're going to do a bunch of transformations, okay? All right, we'll be over that tomorrow. Bye-bye. I gotta make sure this note's set so that you.
Why are you reminding me of that?
No boss, hell no. Oh, you won't stop it. No, you see, it's usually automatically getting set.
If it's not already, she said it might not work. You need a sample?
Yeah, less.
Did you have 10?